Hello, I'm Rich Eisenberg, Editor-in-Chief of Inorganic Chemistry. As part of our 50th anniversary year, we're going to have a series of interviews, and today it is my distinct pleasure to have Professor Fred Hawthorne, who some people will say is Mr. Inorganic Chemistry, here with us to talk about his career and talk about publishing in inorganic chemistry. Fred is now at the University of Missouri. He is a professor of radiology, chemistry, physics, and nuclear science. We'll get to all those titles in a minute. But also, most importantly for us today, he was also the editor of Inorganic Chemistry for 32 years and really brought the journal to where it is today. Fred, it's an absolute pleasure to have you here, and I'm going to start with a couple of questions relating to the journal, and then we'll move quickly into the career part. You began your editorial career with Inorganic Chemistry in 1966 and then became editor-in-chief at a young age in 1969. How did the journal start, and how did it operate at that time?
The journal was originated by Bob Perry, who had an idea that a journal devoted to inorganic chemistry would be a popular publication of ACS if it were established. He then stepped down, and Ed King from the University of Colorado took over after, I would say, about 2 years. And then the journal grew, and the journal became more and more synthetic in nature. And they needed a synthetic type chemist. And so I was asked to be the associate editor with Ed King as editor. And we did that. I think we did that for about 2 years. And then I moved to from UC Riverside, where I began the journal work, to UCLA. And Ed King retired, leaving me with the journal. I immediately got Herb Case, my new colleague at UCLA, to assume an associate editorship. And the two of us ran the journal for about a year, and then we took on Mel Churchill from University of, well, he was at Harvard at that time.
Mm-hmm. Did you think you would do this for 32 years?
No. I know now it's impossible to be a perfect editor. Somebody is going to be unhappy. But yes, right. But I was striving for perfection, which. But it's very much. People ask me, what's it like, and if you've ever run a dairy farm or a chicken farm, where you had animals that had to be maintained on a daily basis. And a dairy farm comes to mind. You have to milk the cows in the morning, milk the cows in the evening, feed the cows, make sure the cows are happy, talk to the cows. These are your animal clients on the farm, which correspond to the authors and referees.
Yeah, I'm not sure I'm in love with the analogy, but it's correct. I'll tell you the
reason
truth.
I chose that is because come hell or high water, you've got to do it.
Yeah. Let me turn to your career. You've had an absolutely extraordinary scientific career, most notably at UCLA, but as you'll tell us, at other places before, and have received accolades, the highest award of the American Chemical Society, the Priestley Medal. Many years ago, you were elected to the National Academy of Sciences. What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part of this? What is it like to be a part At an age when many would contemplate retirement with a record like that, you've embarked on an extraordinary, and I'll put that in quotes, but it really is, extraordinary second career.
I have always worried about retirement as I grew older, and I like chemistry very much, science, scientists, students, everything about it. And to leave that, to arbitrarily say, oh, I'm going to stop doing this and stay home and work in the garden or watch TV or just sit around and vegetate, I couldn't do that. Turns out that throughout this chemical career, I was very interested in boron chemistry, and I was fortunate in that I was able to bring it from an unknown state to a state in which it can be counted upon as a chemical staple, if you will. And one of the applications of that chemistry, it takes advantage of the boron-10 isotope. There are two isotopes, boron-10, boron-11. Boron-10 is present in nature in 20% abundance. And boron-10 has a very high neutron cross-section. Way back in 1936, 4 years after the neutron was discovered in 1932 by Chadwick, a physicist by the name of Locher proposed that nuclei such as boron-10 could be placed in cells that one might wish to selectively destroy, and then that implanted boron-10 is exposed to neutrons, thermal neutrons, which are innocent as well with tissue. When the two meet, then we have a intracellular nuclear explosion and kills the cell. The fission particles being helium and lithium, these are heavy and they don't go very far. So they go about 1 cell diameter. So then boron chemistry's got something to do. I started pursuing this idea about 1960, and we made contributions to this area. This was called BNCT, boron neutron capture therapy. Chemists such as myself made boron compounds which we thought would be selectively taken up by cancer. We found such compounds, but we never had the opportunity to try them out with neutrons. We had playing half a deck.
So the University of Missouri has a special facility and then he called you.
Well, there turns out that there are two medical sources of neutrons that are academically based in the U.S. One is at MIT, and the other is at the University of Missouri in Columbia, where I am now. In the refrigerator, I had a number of compounds which we had proven had some viability as boron target compounds for cancer, but they had never been checked out with neutrons. So I was very unhappy about this cessation of the program without ever having had our materials tested. Okay, so one day I got a phone call from a friend of mine, University of Missouri, a Katish Caddy, and Dr. Caddy is a chemist and a radiation person, imaging and therapy. And he interacted with the nuclear reactor in Columbia. And he was going to, of all things, take over a journal, a new journal to be privately published. And the area of interest was going to be nanoscience. And he knew about my experience with inorganic. And the question was, would I mind coming to Columbia and giving an after-dinner talk to his colleagues and describe what it's like to be an editor. Well, it depends on what day of the week it is. You see, some days are good days, some days are bad days. But I wasn't going to go. I began my academic career at a branch of the University of Missouri in Rolla, which was an engineering school. And I did 3 years of chemical engineering there and then moved on to California, finished up. And I hadn't been back in the area. It's truly a flyover area, right, unless you have something engaging on the ground. But my secretary at the time said, you got to go do this, you know. You can't not do it. So I agreed. And I went back to Columbia, and I was absolutely dismayed by the scope of the academic program available at this campus. At everything, veterinarian school, medical school, arts and sciences, engineering, on and on. We had things that UCLA did not have, nor did any single campus at UC have all this stuff. Furthermore, the people I met were exceedingly friendly and seemed to want to collaborate. And they had a nuclear reactor. And I hadn't been near a nuclear reactor for a long time. And they showed me that. And then the time came late that afternoon to have the dinner at which I was to speak. I hadn't prepared anything. I figured it's going to be about 10 guys and get up and tell a couple of jokes. And I show up for this thing. The chancellor is there, the provost is there, the presidents, everybody is there, and the room is full. And I've got no prepared speech. So finally I was introduced, and somehow I pulled it off. And after about 20 minutes, I sat down sitting by the chancellor. Chancellor said, I know you're not leaving until tomorrow afternoon. Would you mind coming over to my office in the morning, and I'll describe more about the campus. So I agreed. Next morning, I was in the chancellor's office and had a cup of coffee and chatting a little bit, and he said, we would like to collaborate with you scientifically. And so I said, great. I said, you've got tools here that I don't have available, and I could send some of my people here, and we could trade people, trade compounds, techniques. And he said, no, we want you to relocate, to move. And that kind of stopped my clock there. And I said, but I'm 76 years old. He said, well, that doesn't make any difference. He says, yeah, you could do it. Next day I signed on as a director of a new institute at MU. Then I backed up those members of my research group who would move, got all our equipment and all this, went horrendous.
But now you have this wonderful institute.
Now we're there. We got.
And it was dedicated last year.
Yeah, right. Our things that we work on are boron chemistry, medical applications of boron chemistry, which is really quite broad, ranging all the way from BNCT to pharmacology, imaging, the actual structural materials used in medicine, polymers and the like. So there's that aspect, and they built us a building dedicated to the institute, and a neutron beam was attached to the reactor. So within about 2 years, we were in business. Mm-hmm. So I've established a lab there, which probably is good as any lab of its type in the U.S. And as fate would have it, BNCT, had it been developed, could have played another major role in my life. And by that I mean the following. About a year ago, the summer of 2008, I had a lesion under my tongue, which came from pipe smoking. And I'd had that for about 30 years, and it was benign. People say don't worry about it. Suddenly it began to hurt, and I got it checked out, and it was diagnosed as squamous cell carcinoma. Okay, to make a long story short, I had surgery, and lost a significant portion of my tongue, and radiation. I had 35 X-ray therapeutic sessions, and that really affects my voice at some point. But the thing is, that's the existing way of treating this stuff, and most of the time it works. And the point here is that if BNCT had been where I believe it should have been, that is fully developed and available for a spectrum of cancers, then chances are I might well have been a patient for my own stuff. But timing wasn't quite there. But if I ever succeed in proof of principle of BNCT, I can say I've been on both sides of the fence, old-fashioned way and the new-fashioned way. And it's rather ironic that the thing comes back and gets you this way.
Well, let's hope that succeeds. And knowing you, I think it's got a good chance. But let me turn attention to boron, which is really the thread through your scientific life. And it's an element that maybe gets short shrift in our inorganic chemistry courses.
It truly does.
Yeah. So how did you develop your interest in boron, and perhaps even before that, how did you develop your interest in chemistry? Who are the people that shaped Fred Hawthorne?
Interesting. Well, first of all, when I was a kid growing up, I grew up in Kansas and Missouri. My dad was an engineer before World War II. And we moved frequently. We moved every 6 months. I'd be in a different town, different school. So I didn't have many permanent friends. So I had to have a hobby. And in general, what I did was things that had a scientific bent, things like radios and airplanes. And finally, a chemistry set came along. And I was pretty fascinated by that. I kept coming back to that as something to be interested in. Now, most kids, when they're 12, 13, something like that, their contact with chemistry would be make some fireworks, blow something up, burn something up, do something sensational, shake up the neighborhood. I didn't do that. I became interested in how chemistry works, so I started reading college textbooks on organic chemistry. So the time I was about 14, I had a home lab, an organic lab, and I knew quite a bit about organic chemistry. And then World War II was going, and I couldn't get chemicals, so I made many of my own. Interest in organic chemistry was embedded in me. UCLA was a very red-hot organic campus at the time. Saul Winstein was there. Don Cram was just beginning. I signed up and worked with Don Cram, not knowing that in 1987 he'd win the Nobel Prize for his research. So after about 4 years, I finished up there. Then I worked with George Hammond for a year and a half. And, George was another famous organic chemist who invented organic photochemistry as a science. Hammond was a consultant for Roman Haas, and he worked with them in a place called Huntsville, Alabama, which was, as you will recognize, Huntsville was the ground zero for the U.S. rocket program. My first job at Roman Haas was to work as an organic chemist, but work on analytical problems. And part of the policy of the lab was that you had maybe a third of your time could be spent on your personal research, which was a very attractive thing. So I started working on reaction mechanisms of reactions related to explosive synthesis of nitro compounds, nitrate esters and things, and doing analytical stuff on the side. I did pretty well. About, I believe it probably 1956, we had a new manager come in. The old boss, who knew von Braun, went to Philadelphia, went back to Roman Haas, and a new guy, Warren Niederhauser, was sent down to take his place. And Warren was a very clever and experienced industrial organic chemist. So he shook things up, and people who were doing kind of academic things suddenly found themselves doing things that had some practical use. And the program was changed. There was a boron program going on in which synthetic boranes were being prepared on tons and tons of it for use in jet engines for bombers. That program failed, but the boranes were left over. So Niederhauser said, well, we're going to use these in rockets. And he called me in the office and said, I want to do this boron thing, and I need to have a group, and would you like to be a group leader? And of course, I could add another 0 to my salary, and this was an important thing to me then. And now I can have a 5-figure salary. And without knowing anything about boron chemistry, I'd had one little course in inorganic chemistry as an undergraduate. I said, yeah, I'll do it. So, fine. I went out of the office, grabbed a book on inorganic chemistry, and looked up boron hydrides. Toxic, explosive, difficult to prepare. But nonetheless, we started. So I started building a group. And within about 3 years, we had the best group of its type in the U.S. devoted to rocketry. And we had made some important discoveries. Carberines came along, not from our lab, but we deduced the correct structure. Polyhedral anions like B12, H12, 2-, and B10, H10, 2-, were uncovered in our place. And boron chemistry at that time was based upon simple borines, diborane, tetraborane, pentaborane, things which I now equate with alkanes, aliphatic, open chain hydrocarbons. The aromatic boranes, those things that correspond to benzene and other aromatic organic species, had not been discovered, and that's what we found. So we initiated the field of aromatic borane chemistry, and this was serendipity, not planned. It worked because we were careful experimentalists and were able to recognize and characterize new things.
One of the things you might have said to me at some point was that when you started your career, and this may have been the academic side, that you suddenly were in possession of a large amount of boranes that were available and nobody was using.
Well, yeah, the story was Carberry had been developed. Carberry was a icosahedron, spherical molecule. I synthesized biscarberine, where we had 2 of these hooked together, like biphenyl was bicarberine. And I had a little bottle of this, and I took it with me to Wright Patrick Air Force Base to give a briefing to the program manager. And I said, we have biscarberine. Reached in my pocket, pulled a sample out, white crystals. Shook him around, and he said, is that what I think it is? Is it 2 carberines bonded together? And I said, yes. And he says, how much decaborane do you use? Or do you have, rather? Because we used decaborane to make this material. And I said, I've got about 100 grams. And he said, well, wait just a minute. And he went out of the room. 20 minutes later, he came back and said, beginning next week, the Air Force will be shipping you decaborane for your exploratory chemistry, as well as scale up in the pilot plant. And we're sending you a long ton, that's 2,200 pounds of this stuff, free. Okay, so this began to come in 50-gallon drums of vermiculite and about 15 pounds of deca in these drums. And they were in the hallway, they were outdoors, they were all over the place. But we then had plenty of deca to do new chemistry and scale things up. We did make rockets, and we did make rocket motors based on boranes, and we fired these things and they worked. And we couldn't have done that unless we'd had this stockpile.
You mentioned the aromatic boranes. I'm going to ask in terms of your personal reactions and the kind of special moment that we have when you're doing research and something suddenly clicks and you know it.
Yeah.
It may not be the most significant accomplishment of your life, but it clicks and it's one of the most satisfying feelings that you get. You realize you suddenly opened up a whole area, or you've achieved a deeper level of understanding. Tell me about that, perhaps with regard to the aromatic boranes or the dicarbolides.
Very good question, Richie. As I said, we were doing exploratory work, and we had a purpose for running certain reactions, but we really never knew how they'd come out until we analyzed things. And we found that the reaction of certain decaborane derivatives with amines, tertiary amines, gave us a salt, very stable material, unlike anything we'd seen before. And we had the had B11 NMR available, ran that. It was a simple doublet, meaning there's only one kind of boron in it. We did some molecular weight estimations and found that it should have 12 boron atoms, so it's 12 BHs. And it turns out that Longwood-Higgins in England had predicted that B12H12 would be a dye-negative ion and perhaps have aromatic properties. It would be the inorganic, or the borane analog of benzene. Well, that's when the light clicked. This is probably right. And we then found another reaction. We found a species which was B10H10, 2 minus. Among the platonic and Archimedean solids, there's a bicapped Archimedean anaprism, and that's a 10-vertex solid, and we believe that's what the structure was. It fit the B11 NMR perfectly, 2 to 10. I'm sorry, 2 to 8 rather. And and both of these structures were later confirmed crystallographically. But they were stable, and you could do things with them that you couldn't do with a normal borane. In other words, you could cook them with water. It wouldn't hydrolyze. It was air stable. Yet, if you put them in contact with an oxidizer, you'd have an explosive or a propellant, whatever. And about that time, a new material, which proved to be carberane, B10C2, 10 and 2 is 12, which was isoelectronic with B12H12, 2 minus, and that material appeared. The thing that was wrong is that the discoverers had the wrong number of hydrogens. They had 14 hydrogens in the formulation. It's only 12, which we proved in Huntsville. And then, of course, that's obviously isoelectronic with B12H12, 2 minus. So we then proposed an icosahedral structure for the carberane. Very, very interesting. This all kind of fell together, and we were off and running with the area.
I can't let this pass without noting the sort of the apex cleavage reactions that you found, and then from that using the corresponding anion for binding to metals.
Right.
Just decade or so later than sandwich compounds and CP compounds were found.
That was 1965, at which point I had left Roman Haas and moved to UC Riverside, my first teaching job. And we knew that orthocarborane would, and meta for that matter, but ortho is very easily reacted with base to remove a boron atom. So you go from a B10C2 to a B9C2 material. Now, if you have an icosahedron and you pull a boron out, one would predict you would take a boron atom away from the vertex that was nearest neighbor to the two carbons, since these were positive centers relative to boron. If you did that, then you'd have an open 5-membered face. And then if you fool around with the number of electrons and protons, you could come up with an analog for the for C5H5 minus, CP minus, and this would be B9C2H11 2 minus. So predicted that stuff that we got from the base reaction, if treated with a strong base, would lose one more proton, go to a dinegative ion with 6 electrons in a 5-membered ring, which could then be used to form complexes with transition metals. And it worked.
I remember when I was a student and that was coming out. That was really very spectacular.
Really blew me away. And then we did all kinds of metals. And that got the structures, and then we published. And that opened up another area of organometallic chemistry. So you see, we had in boron chemistry now, we had the alkanes, alkynes, the old-fashioned boranes. Then we had the aromatic polyhedral ions, BN, HN 2- series. Those were the aromatic hydrocarbons. And then we had some heterocyclic analogs with carberine and nitrogen and phosphorus in the cage surface. And then finally we put metals in, and now we had organometallic analogs. So we had complete analogy with organic chemistry expressed with the boron chemistry. So that was very, very exciting. So exciting I've never been able to get away from it.
And I think your enthusiasm for that really shows. Let me ask you now, going forward, not for you, which is really impressive, but advice for young investigators, scientists starting out on their careers. What would you tell them? What would you advise? Because your research has taken a very wide arc and has been a really interesting development of an entirely new area. So what would you say to young investigators? What do you think that they should consider in what they do?
I was very lucky. I've been very lucky. Most of the things I get in and out of, I get out alive. The boron, when I got to Huntsville, working on rockets, that was just fortuitous. And boron was undeveloped. H.C. Brown was just beginning to worry about hydroboration. The boranes were just that very reactive, dangerous materials handled in a vacuum line. But I got under Niederhauser's influence in this laboratory, and he turned me loose with this stuff. And I brought it out and used the techniques that organic chemists use, 3-neck flask stirrers and stuff, And that backed up by a ton of decaborane. I couldn't go wrong, you see. I guess what I would say is that luck, being in the right place at the right time, it still plays a major role in what's going to happen to an individual. You can help things along, though, if you are curious. And curious to the point that you will get up out of your chair, get away from your desk, walk out into the laboratory, grab a simple test tube, and try some new things. And I think today students may be embarrassed to do this sort of simple serendipitous research because it's not cool. What's cool is a computer calculations and all. You can compute everything. Why go into the lab? The trouble is computers don't really have everything, and there are many, many surprises out there that are still to be observed. And so my advice is to have a low activation energy for trying new things, and to do so carefully. And we develop excellent skills, analytical skills, if you will. So if you do have some new material or some new reaction, you're able to recognize it as such and figure out what it is, and either reject it or go ahead and pursue it. In recent times, we hear much about nano materials applications, and what you just said is very prevalent. People don't do basic research unless you can say, well, if this succeeds, then I can do this application. The coupling of applications and with basic research is perhaps overemphasized, in my opinion. And the day of another thing is the search for collaborators. Your chemistry is no good unless there's 5 or 10 people working on it, which I think is phony baloney. Of a group of 5 or 10 people, there's going to be 1 or 2 that have major ideas and the proponents of these areas. However, politically correctness prevails, and you can cover ground with a lot of people in different areas if you know what you're doing. But if you don't know where you're going or what you're doing, it's just, there's a lot of people wandering on the desert that don't know what's up. So I think we need more emphasis placed on the single investigator working along with his own group, and if he makes a discovery, then he takes in collaborators and does all this sort of thing. But to go out and recruit a large number of people and then get them all lined up, now we're going to go look for something new, nobody can agree, and I think a lot of time is lost. I think there's still many, many things that are remaining to be discovered of major significance, which could be most efficiently found and developed by 1 or 2 people working together, and not a big army. All of the granting, at least in the U.S. and internationally as well, the granting agencies are people who support research, academic and otherwise, have no, I'll say, sympathy for the lone investigator. They would prefer to have a group, collaborators, plural, and this has become sort of an edict that comes out of granting fun headquarters, and I think this is a mistake.
The lone investigator, by the way, is not a single individual, but is a person working with a research group that can be sizable and
Right.
Is not necessarily an isolated scientist. That person is also quite capable of collaboration.
Indeed, yes.
And you've mentioned that. But for the fundamental, the serendipitous research, perhaps it is the lone investigator that is absolutely key.
You can cover working. Although I had a group in Huntsville, where my first job, I eventually had 17 people in my industrial group, and I began with one lab tech. But all through the ordeal, I always worked in the lab myself, and I had a drawer full of test tubes, and rubber stopples, hypodermic needles. So if I get an idea, I could go out in the lab and try a new reaction. It's easier than I could go to the library and try and find something in chem abstracts that either did or didn't fit the situation. And I think the people that were successful that I've known beginning in the 50s were experimentalists by and large who had this low activation energy to grab some piece of glass, put some stuff in it, and see what happens, and not just make pretty colors, but actually analyze the results, looking for some objective.
Just to sum up, for advice for new investigators, be curious,
Hang
just
loose.
do it.
Yep.
And that's good. Let me return to the journal for a minute.
Sure.
While we do this. You've watched IC, well, you've not only watched, but you've been the major participant as IC has grown to the publication it has today. And I'd like to know your thoughts about publication in the future. We're on the verge of an electronic paperless age, something that we couldn't imagine when we were starting out. How do you see scientific communication progressing, and what advice would you have for young scientists today with regard to publication?
Well, I was thinking about that recently, since many of our journals are no longer going to be published, except for electronic publication. And the growth of scientific information output is stupendous. I mean, I take a number of journals, but I can't read all these journals. I've got papers coming, things piled up. It's impossible. It seems to me like many encounters, many reader encounters that should occur, that if we were doing things correctly and transmitting science in the proper channels for productive purposes, these are not occurring due to the entropy in the system. The probability of the right guy being in the right place, right time, without knowing what he's looking for. You see, another thing related to the test tubes in the lab is browsing in a journal. Now, in the 50s, you had JACS, you had Journal of Organic Chemistry, Journal of Physical Chemistry, and this comes out every month. You can sit down and browse through this thing and actually memorize JACS if you're interested in it. And therefore you know what's going on. It's impossible today. I mean, every week you're getting stuff coming in. not only from U.S. sources, from ACS, but European. So you're overwhelmed. So you almost need another way of indexing or finding areas, subject areas that would be of interest to investigators. You need another middleman, perhaps, or mechanism. Another way of indexing things, because this is what it's amounting to. You've got all this stuff, and you divide it up, and maybe there's 2 or 3 papers here that really are of interest, and you got to look through like 300. You won't do that.
Yeah.
But if the key words are properly chosen, I think this is probably that sort of thing is what's really important, is for the author to accurately.
Yeah. We might be able to do that in terms of virtual journals. We might be able to have, let's say, boron, carboranes, and you'd get all the papers assembled that come on that particular subject. Doesn't allow for the accidental browsing where the paper next to it happens to be the one that you really want, but it's
SciFinder,
SciFinder
is a
great
way of looking at an area, which I think is productive, but it's a hit and miss thing too. But it's a thermodynamic problem. I mean, it's the getting A to find B, and when there's all kinds of B primes and B double primes and decoys.
Right. Let me actually ask you one final question about inorganic chemistry and what you see as the proudest achievements you had with the journal. And I will salute you. This is your record of 32 years will stand well into the future, and it's very, very impressive. But let me ask you what you are most proud of with regard to the journal.
I think, well, I think the growth of the sheer growth of the operation has been impressive, starting from 6 times a year to okay, that's what's going to happen. And I think the best thing an editor can do is to measure success. It is the following: when you're ready to quit, is there somebody out there who you believe is probably better than yourself in this editorial business, who looks at your journal and says, yes, I would not be ashamed to be the editor of that. I'd like to be the editor of that, and that was you, in my case. And so your taking a job was one of the best things that happened to me in the journal. And it's beautiful, Richie. I mean, what's going on now? It's fantastic. It's unbelievable. If I'd seen this 15 years ago, I wouldn't have believed it. But it's grown, it's matured, and the formatting and the editorial process is neat. I think that's the one thing that you can measure is continuity. That's a dynamic. The other things are statistics, so many pages, so many papers, this and that. That and the number, the stature of your authors, and your reviewers, and your readers. But the stature of your authors is something that you can measure, and that's continually improved. But I do believe the continuity of the editorship is the most important thing that has to be satisfied, but not only does it have to be done, it also serves as a measuring stick of how the journal is perceived by the chemical public.
We're now a truly international community. Most of our authors are submitting from abroad, and everywhere I travel outside the U.S. to laboratories, we'll see inorganic chemistry, we'll see our inorganic chemistry calendar, we'll know that we're part of a global community of people that are really interested in the science. I think I'll just close by saying that one of the most important things that you did in your career, that this interview shows, is the wide arc someone's career can take, and the impact and the impact that you can have, starting off with this notion of why did this happen, why did this work, the curiosity, and Fred, I hope that we're going to be curing cancer using BNCT and doing all kinds of great things.
We're going to try.
From current inorganic chemistry, let me say thank you very much for taking time with us today.
Thank you.
And I'm really delighted that our viewers are able to see this interview. And thank you again.
Thank you for the invitation. And it's a great honor to be able to continue to interact with inorganic chemistry and you. Thank you.